After learning the basic notion of the limit of the function, we will extend our lesson about the concept of continuity. Merriam-Webster Dictionary defines continuity as uninterrupted connection, succession, or union. You are going to learn its concept applied mathematically. You should be able to illustrate continuity of a function at a number and on an interval. Determine whether a function is continuous at a number or not, and solve problems involving continuity of a function. Consider the following graphs of a function at number a. We can say that a function is continuous at a point or at a number if we can trace the graph of the function and pass through the point without lifting our pen. If that is so, notice that among the graphs, only the graph in figure 1.6.4 represents a function that is continuous at a. Let us formally define continuity of a function at a point or number. A function f of x is continuous at x equals c if the following conditions are satisfied. First, f of c exists. A number exists if it is defined. Division by zero yields to undefined values. The same with square root of negative numbers. Thus, these cases must be checked. Second, the limit of f of x as x approaches c exists. Based on our previous lesson on limits, the limit of a function f of x exists if the left-hand limit is equal to the right-hand limit. Third, the limit of f of x as x approaches c is equal to f of c. Upon checking whether a function satisfies the first two conditions, check whether the obtained values from these conditions are equal. Always remember that if one or more of these conditions are not satisfied, then f of x is discontinuous at x equals c. We will now determine if f of x equals 3x minus 1 is continuous at point 1. For the first condition that f of c exists, we will use c equals 1 since the given point is 1. So by substituting the value of x in our function, we have 3 times 1 minus 1 and that is equal to 2. Therefore, f of c exists. For the second condition, that the limit of f of x as x approaches c exists. So we will be assigning a certain number from the left of c and from the right of c. Since c is equal to 1, so we will be using 0.9999 from the left of c and 1.0001 from the right of c. For x equals 0.9999, by substitution, we have 1.9997. And from the right, for x equals 1.0001, we have the value of the function which is 2.0003. Take note that this number is approaching to positive 2, and same with this one. Since the left-hand limit and the right-hand limit are equal to 2, therefore the limit of f of x as x approaches 1 is positive 2, and the limit of f of x as x approaches c exists. And for the third condition, the limit of f of x as x approaches c is equal to f of c. From the second condition, we have shown that the limit of f of x as x approaches 1 is positive 2. And from the first condition, we have shown that f of c is equal to positive 2. Therefore, they are equal. Since all the conditions are satisfied, then f of x equals 3x minus 1 is continuous at point 1. This is the graph of the function, and it is clear that we can trace the point 1 without lifting our pen. For the second example, determine if f of x equals x squared plus 5x plus 6 is continuous or not at point -3. Using our calculator, by inputting the function, we generate the graph and point -3 is traceable without lifting our pen. Thus, it is said to be continuous. To formally answer this concern, we will show that the three conditions are satisfied. The value of c is -3, and by substituting -3 to the x of the function, we have 0. Therefore, f of c exists. For the second condition, limit of f of x as x approaches c exists. From the left of c, we will use x equals -3.0001. And from the right of c, we have -2.9999. After substituting these respective values of x, we have from the left 0.0001 and from the right -0.0001. Both are approaching to 0. Therefore, the limit of f of x as x approaches -3 is 0. Therefore, limit of f of x as x approaches c exists. And for the third condition, the limit of f of x as x approaches c is equal to 0, and the f of c is also 0, so they are equal. Satisfying all the conditions, then we can say that f of x equals x squared plus 5x plus 6 is continuous at point -3. In geography, it has been held that the layers of the interior of the Earth are not continuous, as the result of studying the behavior of seismic waves. In between the crust and the mantle lies the Mohorovičić discontinuity, or simply MOHO, and in between the mantle and outer core is the Gutenberg discontinuity. In mathematics, function is sometimes discontinuous. To dig it deeper, let's be acquainted with the different types of discontinuity. The first type is the removable discontinuity. A function is said to have a removable discontinuity at x equals c if f of c exists and the limit of f of x as x approaches c is not equal to f of c, either because f of c is undefined or the value of f of c differs from the value of the limit. Let's consider now this example. Determine the function g of x equals 3x squared minus 4x plus 1 all over x minus 1 if it is continuous or not at x equals 1. The first condition, which is g of x exists, is not satisfied because after substitution, it is found out to be indeterminate. Even if the limit of g of x as x approaches positive 1 exists, still the first and the second conditions are not equal. Thus, it is a removable discontinuity at point 1. It is obvious on the graph that at x equals 1, there is a gap on it. The next type is jump discontinuity. A function is said to have a jump discontinuity at x equals c if the limit of f of x as x approaches c is not equal to f of c, for c any positive integer. This type of discontinuity can usually be found on piecewise function. Unlike the removable discontinuity, all possible values of x are defined, omitting the possibility of having indeterminate or undefined expression. Consider now the example. Determine whether f of x equals 3 if x is less than or equal to 0 and f of x equals x minus 1 if x is greater than 0 if it is continuous at x equals 0. It is clear from the graph that f of 0 is positive 3. On the other hand, the limit of f of x as x approaches 0 does not exist. Therefore, they are not equal. So, the function is discontinuous at x equals 0. And lastly, the infinite discontinuity. This type of discontinuity exists when one of the one-sided limit of the function is infinite. In other words, the limit of f of x as x approaches c from the right is positive infinity, or one of the three varieties of infinite limits. If the two one-sided limits have the same value, then the two-sided limit will also exist. Graphically, this situation corresponds to a vertical asymptote. Many rational functions exhibit this type of behavior. Let's consider now the example f of x equals 1 over x. Kindly observe its graph on the right. We will show the three conditions to prove if it is continuous or not. The first condition, f of c exists. Since the value of c is 0, then we will substitute the x by 0. So we have 1 over 0 and that is undefined. Therefore, f of c does not exist. For the second condition, the limit of f of x as x approaches c exists. Take note on the graph that the limit of f of x as x approaches 0 from the left is going to negative infinity, that is going downward. Therefore, the limit here is negative infinity. And for the limit of f of x as x approaches 0 from the right, take note the behavior of the graph that it is also going to positive infinity. Therefore, the limit of f of x as x approaches 0 from the right is positive infinity. Since the left-hand limit and the right-hand limit are not equal, so the limit of f of x as x approaches c does not exist. And for the third condition, that the limit of f of x as x approaches c is equal to f of c. Although they are both does not exist, but still, the answer is not existing. Since the three conditions are not satisfied, the graph is discontinuous at x equals 0. In short, if all the three conditions are not satisfied, then a function is said to be discontinuous at a point c. Let's proceed now to the continuity of a function at an interval. A function can be continuous on an interval. This simply means that it is continuous at every point on the interval. Look at the figure 1 on the left. In this figure, we can create different types of interval. We have this open interval, closed interval, and half-closed interval. For open interval, the endpoints a and b are not included. In this case, since this is open interval, these 2 points are not part of the values of x. For the closed interval, we are using bracket. So meaning to say, these 2 points are included in the values of our x. For the half-closed interval, we are using one parenthesis on the other side and bracket for the other side. In this case, b is included and a is not. And for the second, a is included, b is not. There are two concepts which are important in determining whether a function is continuous at the endpoints of closed interval, and that is by utilizing the definition of one-sided limit. And here is the definition of this one-sided limit. These are the known facts on continuities of function on intervals. Polynomial functions are continuous everywhere. That means in a monomial, binomial, trinomial, and other polynomial functions, intervals are always continuous. Is the function f of x continuous on the interval -4, -1? By this known fact that the polynomials are continuous everywhere, and since f of x is trinomial, then it should be continuous on that interval. We will show later the process to prove that this function is really continuous at this interval. The absolute value function f of x equals absolute value of x is continuous everywhere, just like the polynomial functions. Rational functions are continuous on their respective domain. The radical function f of x equals square root of x is continuous on the half-closed interval 0 to positive infinity. In f of x equals square root of x, The restriction here is that the radicand should be greater than or equal to 0, because when x is less than 0, the resulting value is an imaginary number. Thus, its restriction is that x must be greater than or equal to 0, or within the interval 0 to positive infinity. For our illustrative example, using the given graph, determine if the function f is continuous on the following intervals. Again, in the graph, once we can trace it within that interval without lifting the pen, then it is continuous on that interval. For instance, the open interval -1, +1. We can trace the graph without lifting the pen, so it is continuous on that interval. Similar is true for B and C. To prove if a certain function is continuous at an interval, the following condition must be satisfied. For instance, in letter B, open interval, if f is continuous at every point x in open interval AB, meaning to say, we will be using any value of x within the interval AB to test whether it is continuous or not. For letter E, the closed interval AB, f is continuous on both half-closed interval. We will be using the two endpoints to prove that on that points, the function is continuous. For example, is the function f of x, x squared plus 5x plus 6 continuous on the closed interval -4, -1? Our answer a while ago is yes. We will be showing here the entire process to prove that this is really continuous on that interval. Take note that for the closed interval, a function f is said to be continuous if it is continuous on both half-closed interval. It must be continuous in the left endpoint and the right endpoint. Since the interval is -4, -1, the left endpoint is -4 and the right endpoint is -1. We need to show that at x equals -4 and at x equals -1, the function is continuous. First, we need to test the left endpoint -4. So for the first condition, f of c exists. By substituting the value of x, which is -4, we have the answer of +2. Therefore, f of c exists. For the second condition, we are assigning x to be -4.0001 and -3.9999. And from the result, the left side is approaching to +2 and the right side is approaching to +2. Therefore, the limit of f of x as x approaches -4 is +2. Here, we prove that the limit of f of x as x approaches c exists. And for the third condition, we have shown that the limit of f of x as x approaches -4 is +2, and that is also the value for our f of c. Since all conditions are satisfied, then f of x equals x squared plus 5x plus 6 is continuous at endpoint -4. Here is the entire process for testing -1. And all the conditions are satisfied here. Since all conditions are satisfied, then f of x equals x squared plus 5x plus 6 is continuous at endpoint -1. We have shown that the function is continuous on the left endpoint -4 and the right endpoint -1. Therefore, the function f of x is continuous on the closed interval -4, -1. Another example, check if the function f of x equals square root of x plus 3 is continuous on the closed interval -4, +1. In a radical function, the radicand must be greater than or equal to 0. In this function, our radicand is x plus 3, and the restriction for the radical function is that the radicand must be greater than or equal to 0. We will copy the radicand and that is greater than or equal to 0. And by using the additive inverse, x here is greater than or equal to negative 3. This function is defined if the values of x are from negative 3, negative 2, negative 1, and so on, since x is greater than or equal to negative 3. And since the interval includes negative 4, and it is not greater than or equal to negative 3, then it is sufficient to say that such function is discontinuous on that interval negative 4, positive 1. The solution shows that f of c when c is negative 4 does not exist. Also, the limit of f of x as x approaches c is not a real number and is considered does not exist. All the three conditions are not satisfied. For the second part of the solution, it is shown that f of negative 1 is positive 2. With that, f of c exists. The limit of f of x as x approaches c also exists, which is equal to positive 2. Even if the function is continuous at endpoint positive 1, it cannot be continuous on the interval negative 4, positive 1, as shown in the graph. Consider now the graph of the function f of x equals 1 over x squared. Note that the function is not defined at x equals 0, since this is the asymptote of the graph. But we can check the behavior of the function as x approaches 0 intuitively. We first consider approaching 0 from the left. Observe that as x approaches 0 from the left, the value of the function increases without bound. When this happens, we say that the limit of f of x as x approaches 0 from the left is positive infinity. Therefore, the limit of 1 over x squared as x approaches 0 from the left is positive infinity. Observe now the graph on the right. The same behavior with the graph on the left. As x approaches 0 from the right, the value of the function increases without bound. The limit of 1 over x squared as x approaches 0 from the right is also positive infinity. Since the left-hand limit and the right-hand limit are equal to positive infinity, thus the limit of this function exists, and that is, the limit of 1 over x squared as x approaches 0 is positive infinity. The behavior of the graph of f of x equals 1 over x was already tackled in this video, and it was found out that the limit of 1 over x as x approaches 0 does not exist. Consider the piecewise function and determine if it is continuous at an open interval positive 4 to positive infinity. We will only utilize the condition if x is greater than 4, since the interval being asked here is from positive 4 to positive infinity. Note that on the open interval a to positive infinity, f is continuous at all x greater than a. Since a is positive 4, we will substitute a number greater than 4 as the value of x. So let's have x equals 5. Why we choose positive 5? From the condition this is greater than 4, so any number greater than 4 can be the possible value of our x. And in this case, we are using positive 5. Since we are using x equals 5, so the value of our c is also positive 5. So we are assigning numbers from the left of c and from the right of c. And we have shown that the three conditions are satisfied. Since all conditions are satisfied, then g of x is continuous on the open interval positive 4 to positive infinity.